All right. Thank you all for your patience. We're going to start the session of the hands-on simulation series. So this is the fifth part of the hands-on simulation series, which will be covering the topic of fluid-induced noises and fluid-induced noises and forces. So my name is Yafis Siddiqui, and I'm the technical pre-sales team at Maya HTT. And so for today's presentation, it's going to be me and my colleague Mario who will be presenting for us today. For those who are joining us for the first time, let me give you a quick introduction to what this series is all about. So the Hands-on Simulate series is a six-part series aimed at providing users a hands-on experience with Simcenter STAR-CCM+. In this series, we will be solving some of the toughest industry problems using the tool's advanced capabilities. So we started this series with 4 predetermined sessions and then selected 2 based on suggestions provided by you all. So as I mentioned before, the session that is going to be covered today is going to be flow-induced stresses and noises. We are going to have the last installment of this series on mesh motion and adaptation that will cover the overview of mesh motion and adaptive mesh technology in STAR-CCM+. So without further ado, I'm just going to run through the agenda for today's session. So the session will begin with fluid structure interactions, and my colleague Mario will be presenting the FSI capabilities within STAR-CCM+. So I will be presenting the second part of this workshop, and that will be on acoustics. So the main focus of this session will be the multi-physics capabilities within STAR-CCM+. So without any further delay, let's start the session with Mario. Mario, take it away.
Thank you, Yafis. I hope you can see my screen. So let's begin. The fluid structure coupling describes a class of problems where the state of the fluid domain depends on the state of the structure domain and vice versa. Mathematically, FSI is a surface coupled problem. Let's look at its formulation. The blue equation here defines the dependency of the state of the fluid domain on the structural displacement at the interface. The red equation here represents the state of the structural domain dependency on the fluid pressure at the interface. And the gray equation over here represents the compatibility of the 2 equations, that is displacement and the pressure, and it must be same at both sides of the interface. It is important to note that there are multiple levels of coupling between solids and fluids. Let's see what that looks like. The first animation here shows us a wave hitting an oil rig. The displacement of the structure is probably very small compared to the other length scales in the simulation. Therefore, the impact of the structure deformation on the fluid can be assumed to be small as well. Essentially, it's a flow where the fluid is not affected by the deformation, but the structure is definitely affected by the fluid pressure. This type of coupling is a one-way coupled, that is fluid independent, structure dependent. The second animation here shows us a linear peristaltic pump. A series of mechanical fingers are pressing down the tube walls in a sinusoidal form. This sinusoidal wall motion generates a pumping effect. Here, the structure is not affected by the fluid pressure, but the fluid is affected by the structural deformation. This type of coupling is a one-way coupled, that is structure independent, fluid dependent. The third animation here shows us how a glue bottle is being squeezed. A typical engineering question might be how hard a consumer must press the glue bottle to squeeze out a certain amount of glue. The impact of the structure deformation on the fluid is certainly high. The impact of the fluid on the structure is certainly as well. This is a two-way coupling. However, there are different degrees of two-way coupling. The third one, the point number 3 over here, is a static equilibrium configuration where there is a static deformation of the structure and no dynamics involved. The fourth one is a weakly coupled one. Usually an explicit solver coupling is sufficient. And the fifth one is a strongly coupled. Usually an iterative or an implicit solver coupling is required. Before we jump into the hands-on workshop, I would like to give you a quick introduction of the solid stress solver in STAR-CCM+. Firstly, let's start with the solver. STAR-CCM+ has an inbuilt finite element solver to resolve the solid stresses. This solver is used to resolve electromagnetics and viscous flows. With meshing, we can only resolve 3D solid elements. We cannot resolve 2D, 1D, or 0D elements when running a structural simulation. However, we can connect STAR-CCM+ with Simcenter Nastran to include such elements. You have tet, hex, pyramid, and wedge elements in both linear and quadratic discretizations. The meshing for solids is no different than fluids. It leverages the fully automated pipeline workflow. With regard to the material models, you can model isotropic, orthotropic, and isotropic linear elastic models, and also isotropic non-linear elastic models. You also have Rayleigh damping model that includes a numerical damping that reduces unwanted numerical oscillations. Lastly, I would like to introduce you to the concept of segments. These are the locations where you can apply your structural loads and constraints. You can apply them either on a point or a surface. You can also apply a prescribed displacement as well as model a cyclic symmetry. Now let's jump into a simple beam analysis and show how that can be modeled in STAR-CCM+. This example here is set to illustrate various Simcenter STAR-CCM+ features for computing deformation, strain, and stresses in solid regions. The case under study here is a cantilever I-beam loaded at its free ends. The displacement that results from the loading are assumed to be small so that the load displacement relationship remains linear. So now let's jump onto the tool. Firstly, let us go ahead and import the surface mesh. For that, I'm going to click on File, Import Surface Mesh. We do say that we are importing a surface mesh. Basically, we are importing the CAD with a surface tessellation on the surface. Select the file, click Open. I'm going to tick mark Open Geometry Scene and click on OK. And we can see that the file has the part that is the I-beam has been imported. The next step is to assign parts to regions. So I'm going to go ahead and open the geometry tree. And we have the beam present with all the surfaces over here. I'm going to right click on the beam and click Assign Parts to Regions. The beam is already pre-selected, and I'm going to select Create one region for each part, and also create a boundary for each part, that is the default one, and click Apply, and close this tab. The next step for me would be to go ahead and create a continuum, that is the physics continuum. So I'm going to right click on the continuum, create a new physics continuum. I'm going to go ahead and rename it to beam physics. This is where we select all the models which are necessary for the simulation. The next step is to select the models. It's going to be a three-dimensional analysis. We are going to have a solid and a steady state analysis. And we are going to run a solid stress simulation. So I'm going to select a solid stress model. And that's about it. I'm going to close this. Let us open the models tree and have a look at the materials that are selected as default. We have aluminum, which has been selected as a default. So what I'm going to do is I'm going to go ahead and replace the aluminum with a more reliable material for a beam, that is a ferritic stainless steel. This is the STAR-CCM+ materials library. You can anytime add more materials over here or use the existing ones and run your simulation. So I'm going to select ferritic stainless steel and click on OK. Now the material has been replaced. So the next step is to go ahead and create a materials law model. I'm going to right click on the material laws, create a new material law model. And I'm going to rename it to isotropic linear elastic. The next step is to select the models necessary for this particular material property. I'm going to select a new model over here. We are going to select linear elasticity and isotropic linear elasticity. And then now we need to assign the ferritic stainless steel with this particular material law model that we just created. So I'm going to just select it over here. And we can see that everything is populated. We have a density of 7,500 kg per meter cube. We have a Poisson's ratio of 0.3 and a Young's modulus of 211. So the next step for us is to go ahead and assign loads and constraints. Before we do that, let's close all these trees over here. Which are not necessary. Yeah, so we have the beam model which we imported. So I'm going to take you through the different parts of the beam and what boundary conditions are we going to assign. So we have the free side over here, which is the lower flange, the upper flange, and the web. The free side is going to be the space or the point where we are going to apply a shear load of 800 Newton in the negative Y direction. On the other side, we have the wall side, that is the wall side lower flange and the wall side upper flange. The wall side lower flange and upper flange, we are going to assign a normal displacement to these two. And the wall side web is going to be assigned a fixed boundary condition. And let's go ahead and create these constraints. So for that, what we're going to do first is we are going to right click on the beam and create segment. That is a surface segment. I'm going to rename this to shear load. And the next step is going to be to select the places where we are going to apply the shear load, that is the free side of the beam. Click on OK. And over here, we have the type, which is a load and a constraint. Type property allows you to specify the type of condition, that is either it can be a load or a constraint that is applied to the selected part surfaces. That the ones we selected right now are the free side, and we are going to select a load for it. We're going to go ahead and open the tree. And in the solid stress, we are going to select force. We have different kinds of solid stresses over here. We have force, pressure, and traction. For this analysis, I'm just going to select force. And in the physics values, I'm going to specify minus 800 Newton in a negative Y direction. And that is done. So the next step for me is to go ahead and create a new segment, a surface segment. And this is going to be the surface segment for the web constraint. That is, we're going to create a fixed web constraint. I'm going to rename this one to web constraint. The surfaces which we are going to select are going to be the wall side web. Unlike the last time, this time the type of load, the type is going to be the constraint. And in the solid stressed loads, if you open this tree, we are going to specify fixed. It is already a default value. And the last segment which we are going to create now is going to be a surface segment for the flange constraint. Quickly rename this to flange constraint. I'm going to go ahead and select the wall side, that is the upper and the lower flange. And the type is going to be constrained. And lastly, the solid stress loads is going to be normal displacement. And the normal displacement value is going to be, let's leave it at 0. So the next step for us is, let's go ahead and create a mesh. So let's close these trees, create a new operation. Right click, new, meshing operation. And we're going to go ahead and create a directed mesh operation. Directed meshing is basically a method for generating a high quality swept meshes on the geometries in Simcenter STAR-CCM+. The method operates by sweeping a mesh from the surfaces of a geometry through its volume onto a target surface, from the source surface to the target surface. And that's what we're going to do now. Create a directed mesh, select a beam as the part, So I'm going to right click, edit the directed mesh. And this opens the window for the directed mesh settings. So we have different settings over here. Firstly, we have the source surfaces, where I'm going to select one section of the I-beam, one side of the I-beam, which is the wall side, which is the source side, and then the target surfaces. The target surfaces is going to be the other corner, that is the free side of the I-beam. In the connected parts, we have already selected the beam, so it's there. The next job is to create a source mesh. For this, we are going to go ahead and create a patch mesh. This is basically creating a surface mesh which we would like to sweep across the entire volume. In the patch mesh, I'm going to select beam and click on OK. So let me reorient this. So the first option, which is the flag symbol over here, you can see on the left-hand side of the screen, it is an auto-populate feature edges with patch curves. On clicking this button, automatically we have the corners as well as the patch curves auto-populated. And I'm going to click on that now. So we have the corners highlighted now. The next option, so basically we would like to create a few more splits, and the scissor option on the screen, which you can see, is used to split the specified patch curve. So I'm going to use that and split the existing patch curve. Select 4 points right above the existing points on the screen, 2 on the bottom. So maybe it's random points. So let's go ahead and specify the correct coordinates for these points. It is going to be 0.0028 in the negative x direction. I'm going to copy this for ease. The point on the right side is going to be plus 0.0028. Click apply. The bottom one again is negative 0.0028. So basically we are reorienting the points to be perfectly in line with each other. And the last one over here. So we have created the patch points. Now the next job is to use the create patch curve option. So for this, it's the second button after the flag. So we are going to start from the outer end. Sorry, it's not the inner end. Let's start from the outer end. Click escape if you want to deselect, and we are going to select again. Start from the outer end, the bottom point, the right point, and the top point. Now you can see that we have created a closed entity for the patch curve. Similarly, we will have to perform this on the lower side as well. Start from the outer end. Move up, right, and bottom. And now we have, as we can see that we have created a closed entity of a patch topology over here. So we can move ahead with the next step, that is creating a patch mesh. Let me zoom out. Change from patch topology to patch mesh. This is where we specify the number of divisions that we would like to have on these patch curves. So I'm going to go ahead and select these patch curves which are similar in length and assign the number of divisions together for them. That is going to be 7 divisions for these. Click on apply. Select the longer edges now. Number of divisions specified as 19 for these. And lastly, the smaller ones which are remaining. What you can observe is when you select these edges and specify the number of divisions, they turn black. It means that the number of divisions for these particular edges have been specified. And once we have specified it for all of them, number of divisions 1 for these, you can see that automatically the patch mesh has been created on one surface. So what I'm going to do is, this is done. We have created the patch mesh on the source surface. I'm going to close this. And I'm going to specify. So basically the next step is we need a mesh in between to an entire volume. So we need to specify the number of divisions that we need between the source surface and the target surface. And that's what I'm going to do now. For that, I'm going to create a mesh distribution, a new volume distribution. Select the beam. And in volume distribution, we have an option which says number of layers. And over here, I'm going to specify 70 number of layers. And this is how we have created a directed mesh, and it's done. So the next step is to close the directed mesh tab, and right click and execute the directed mesh. This just takes a second. And we have the directed mesh completed. I'm going to go ahead and change the representation on the screen from geometry to volume mesh. And also we need to tick the mesh tab over here in the surface so that the representation appears on the screen. You can see that a clean directed mesh has been created in between. Just like how we started on the source surface, it has been extruded or swept all the way to the target surface. And we have the mesh created. Now, before we run the simulation, let us go ahead and create scenes and reports which we need to maybe extract the results from. The first thing that I'm going to do is I'm going to go ahead and create a scalar scene and rename it to stress. This is going to be a stress scene. And when I select scalar, I'm going to select instead of automatic smooth filled, it's going to give a smooth profile of the scalar. The next thing is to select the parts for this particular scene, which is the only part that we have, the beam with its surfaces. Let's select the scalar field function, which is going to be the stress tensor in the laboratory K, K. And lastly, let's go ahead and select the units to be megapascal instead of pascal. So we have a scalar scene which is created for stress. Let's create another scalar scene for displacement. Rename it quickly to displacement. Before we go ahead and do any other settings, we need to go ahead and create a vector wrap to represent the displacement. So I will explain it to you. So what we're going to do is we are going to go ahead and create a derived part, right click, wrap, and vector wrap. So basically a vector wrap is a vector wrap surface is a part that modifies the input surface point coordinates by moving the points along the selected vector multiplied by the scale factor. It is a feature used to show mechanical deformation. So let's go ahead and create this vector wrap. The input parts are going to be the beam. This is how we are going to represent the deformation of the beam in the y direction. And the vector is going to be displacement. That's what we want to represent. Let's activate auto scale as well. We don't need a displayer as we already have created a displayer of displacement. So no displayer. Click on create and close. In the displacement tab, let me go ahead and create another surface to show the original geometry. So let's create an original geometry which is transparent and the displaced geometry. So with the displacement as a scalar. So let me go ahead, right click, create a new displayer for a surface. And in this, I'm going to select the opacity. So basically make it transparent of 0.2. And in the parts, let's select the beam or the initial representation of the beam. Click on OK. Let's go back to the scalar, that is displacement. As usual, let's select smoothly filled. And in the parts, I'm going to go ahead and select the derived part that we have created, that is the vector wrap surface. Click on OK. And the scalar field is going to be displacement in the laboratory J direction. So we have created another scene for basically for one for stress, the other for displacement. Now quickly let us create two reports basically for the stresses at 2 points. For this, let's go ahead and create two probe points which we would like to have. So I'm going to right click on the derived parts and create two probe points. Let me rename this point. Okay, let us rename it later. Let's select the parts that is going to be the entire beam that we have as an input part, all the surfaces of the beam, because the probe point is going to be on the beam, and the coordinates of the point that we would like to have, that is 50, 100, and 0. So basically, I'm going to create the first point, which is going to be on the corner of the wall side. 50, 100, and 0. Click on no display maybe, and click create. And then let me close the scene. Let me rename this. Let us have a look at the point. So it's on the wall side at the corner, and that's why we will name it maybe as corner point. Right click, rename. Corner point. So next step, we have the point, probe point. Now let's go ahead and create a report for this particular corner point. So I'm going to right click, new report. It's in users. We are going to create a maximum report for this case. I'm going to select, rename this first quickly as corner point itself. Sorry, let's rename it to stress K, K. And the field function is also going to be the stress tensor in K and K direction. Laboratory K, K. Click on OK. And we have, let's activate smooth values. And lastly, let's select the parts for this particular report. That is going to be the derived part of the probe that we have created on the corner. Click on OK. Similarly, let's create another point on the wall side at the center, that is near the web of the beam. So for that, what I'm going to do is, to make things easier, I'm just going to copy the corner point and create a duplicate of it by pasting it in the same place. So let me rename this to midpoint and specify the coordinates to be 0, 0.1, and 0. 0.1 in Y, and again 0, but all these are in meters. So just I'll have to type the letter M over here. So that is done. So we have the midpoint. Similarly, let me create a duplicate of the report as well for the stress at the midpoint. I'm going to copy it and create a duplicate of the report and rename it to stress K, K, maybe near the fixed constraint, that is near the web. And in the parts, what I'm going to select is the midpoint, which we just created by creating a duplicate. And that's about it. So now we have the physics and the mesh setup. The next step is basically to set up the stopping criteria and run the simulation and have a look at the results. So what I'm going to do is I'm going to go ahead and set the stopping criteria. So basically the maximum steps, I'm going to specify it as 2 steps, that is sufficient, and specify a force criterion as well, and set the minimum value maybe to just 1e minus 6. And click run. That's about it. So basically it just takes a second to run the simulation because it's just 2 steps that we are running. Let's have a look at the residuals. Yep, the solution is completed. Now let's have a look at the results. So firstly, let's have a look at the displacement by looking at the views which are already pre-stored. We can have negative X and positive Y direction. That would be a good way to observe the deformation. So what you can see on the screen is that the beam has been deflected in a negative Y direction for about minus 4.663 millimeters. Let's have a look at the stress as well next. on the scene which we had created. Let me store this current view. We can use it later. So we can see that the stress in the K, K, stress sensor in K, K. So I'm going to use the view which we just stored and represent this on the screen. You can see the stress is more on the fixed end, which is natural. And let's have a look at another stored view maybe, which is the isotropic view. So let us run the report stress K, K, that is at the corner point. Run this report. Scroll all the way down. It is 17.4 megapascal. The next thing is to run the report at the midpoint. Let me zoom in and show you where exactly the midpoint is. So over here, it's natural that the stress is going to be more compared to the corner point. I'm going to run this, and it is 18.6 megapascal. This marks the end of running a solid stress demo of an I-beam for computing maybe the deformation and the stresses in solid regions. So next, a very common FSI problem is the flow-induced vortices. In this example, the flow around a square structural member results in the formation of von Karman vortices, which induce oscillatory vibrational forces on the structure. I will now showcase how this model was set up in STAR-CCM+. Know that this is a two-way FSI model that leverages the mesh morphing technology to capture the deformation. So let's begin. This is again another file which is already open. So we have the geometry parts, the bar which is present with its surfaces. We have the base, which is going to be modeled as a fixed end for this particular bar. We have the bottom, sides, and the top. These three are modeled as walls itself. And then we have the symmetry plane, which is going to be a symmetry boundary condition. Now let's have a look at the domain, that is the fluid domain. In the surfaces, we have an inlet, which is a velocity inlet with 11.2 meter per second velocity, which we're going to specify. This is a pressure outlet. We have the symmetry over here, which is going to be a symmetry plane. We have the surfaces. These surfaces are going to be the interfaces, which are going to be common between the fluid and the solid region. And at last, we have the bottom, top, and the wall. Basically, these three are the wall boundary conditions. So let us quickly go ahead and create the continua or the physics continuum for this analysis. We will have to create two continuums, one for solid and one for fluid. So let's go ahead and create a new continuum first for fluids. I'm going to rename this one to fluid. Let's select the models for the fluid domain. It's going to be a three-dimensional analysis. It's going to be gas. Since it is a slow speed one, we are going to select segregated flow. It's going to be constant density. And because it's a transient analysis, I'm going to select implicit unsteady and turbulent model. And because the auto-recommended models are already selected, what happens is when we select the turbulent model, it automatically selects the Reynolds average Navier-Stokes equation. So what I'm going to do is I'm going to deselect RANS and show you we have different models. I'm going to select the large eddy simulation for this one. And then solution interpolation at the last from the optional models that we have, that is the extra models that we have, and click close. Also, let's go ahead and create another continuum for solids. Create a mesh continuum. Rename this to solid. Let's select the models that are necessary for the solid simulation. It's going to be three-dimensional again. We're going to select solid as our material. It's going to be implicit unsteady, just like what we selected for the fluid domain. We are going to select solid stress because the member is going to be stressed. We are going to select fluid structure coupling because it's going to be a FSI problem, and also solution interpolation over here in the optional model, and click on close. Let's have a look at the material that is selected. Let's open the solid tree. In the solid, we have aluminum, which is going to be the default material, and let's leave it to that. In the material law model, just like we did last time, let's go ahead and create a material law model for this as well. It is going to be linear elasticity. and isotropic linear elasticity. And we are going to specify aluminum with this material law 1 that we just created. In the drop down, you're going to select material law 1. And lastly, let's select the right models for the right regions which are present. We have the density of 2,700, maybe we have the Poisson's ratio of 0.33 and the Young's modulus of 68,000 megapascal. That is done. So lastly, let me open the regions tree and specify the right physics for the right regions. For the bar, it's going to be the solid region. And for the domain, it's going to be the fluid region. The next step is to have a look at the meshing. We are going to create a directed mesh, which is already created. I'm going to open the mesh scene over here. You can have a look at the mesh. If I zoom in, the solid body has a very coarse mesh, but it's still a directed mesh. And let me zoom in near the fluid medium. You can see that there is a different sized mesh. It is very fine near the solid medium, whereas it slowly coarsens out as it moves away from the solid medium, that is in the fluid medium. So let me show you the meshing that is already created. We have two meshes, one for bar and one for domain. Let's begin with the bar mesh. I'll quickly run you through the bar directed mesh that we have. Let me reorient the model. We have the source surface over here and the target surface on the other side. We have in the connected members, we have the bar which is present. And let's have a look at the patch mesh that is created. That is creating basically a closed entity. You can see that the patch mesh we have already created a closed entity over here. Let's have a look at the patch. We are in patch topology. Let's jump into patch mesh and see the number of divisions that we have. The longer members have 20 divisions. The horizontal members over here have 5 and the other side have 6. And the vertical members over here, the smaller ones, have 5 divisions. So let me close this. And in the volume distribution, we have selected the entire beam and the number of layers are going to be 5 in between the source and the target face. So let me close the directed mesh. The next thing which might be interesting for everyone is to have a look at how the domain mesh was created with these volumetric refinements. I'm going to edit this. We have, just like we always had for the beam, solid stress beam representation model, we have the source surface, which is on the one side. We have the target surface on the other side. We have the entire connected parts, that is the domain, which is present. But when we define the patch mesh, this is where we need to specify some controls. And I'm going to show it to you now. So let us jump into the patch mesh directly. First, let's have a look at the smaller segments over here, which have been specified as constant divisions. All these which you can see on the screen, which are highlighted, are constant divisions. But if we have a look at the other ones or the other edges, which I'm going to select now. You can see that the type is specified as one-sided hyperbolic. We have different types of distributions which are present. We have a constant, one-sided geometric, one-sided hyperbolic, or maybe two-sided hyperbolic. So what one-sided hyperbolic stands for is the spacing which is specified over here at starts at 0.02 meters. Let me select the longer edge as well. It has 100 divisions. Let me zoom in. You can see that at the beginning, the spacing starts at 0.002 meter and slowly increases as it moves towards the outer side. And this is how we have specified the type of distribution or the type of divisions for all the other side other than the smaller edges, which are specified as constants. So we have 100 divisions over here. So the mesh slowly increases from 0.002 meter, and as it moves outside, it slowly grows. So this is how we have defined the patch mesh. Let's have a look at the volumetric distribution. The total number of layers between the source and the target is going to be 50. And I'm going to close the directed mesh. So the next step is to have a look at the boundary condition and the stopping criteria which are specified. So let's do that. Let me go ahead and open the regions. We have the bar in the bar, we need to specify a fixed boundary condition for one end of the beam. And for that, we are going to specify that in segments. There's a surface segment which is created. As you can see, the base of the bar is highlighted. And if I open the tree and show it to you, it is going to be a fixed boundary condition. That is done. So we need to specify a motion, that is a motion for the bar. So basically the bar is free to move when the air is flowing on it. So basically where in physics values, we have something called as motion specification, and this is set to solid displacement. So basically where do we define all the motions that we have? So let me scroll down. All the motions are defined in tools all the way to the bottom. We have something called as the motion tab over here. We have all different kinds of motion over here, right click, new, and we have rotation, we have translation, we have rotation and translation, various forms of dynamic fluid body interaction motion. For this one, I'm going to select solid displacement over here, which is already created and which is selected on the top as well. Let me show you. This is the one which is created, solid displacement, and that is the one which we have specified over here in motion specification. The bar, let me go to the boundary conditions of the bar. We have the first one, which is the bar/domain, which is a mapped contact interface, which is going to be the common region between the solid and the fluid region. We have the surface, which is for which we have to define the stress/displacement. Let me open this surface, which is basically modeled as walls, but the stress/displacement is going to be free. So basically the bar is free to move. And then lastly, we have the symmetry boundary condition over here. Let us have a look at the domain boundary conditions that we have specified. In the domain, we have, let's go to the physics values. Let me scroll down, physics values, and we have the motion specification, which is defined as morphing. So this is defined in tools as well. All the way, we have selected morphing over here. Let me scroll down and go to tools. Just like we did for solid displacement, there is morphing defined over here, which is a region-wise morphing. Basically, a morpher motion allows you to account for the effect of the moving boundaries on your analysis, if your analysis is basically a transient simulation. The morpher can be used, for example, to simulate a motion of a bar over here as a result of wind, where the boundaries are not changing the shape, but the mesh vertices must morph or move to accommodate the movement. The morpher can also be used, or it can also be applied in cases where the shape of the boundaries is changing. For example, building up of ice on an aerofoil. We will cover this morphing of meshes in the next episode of the Hands-on Simulate series in much more detail. So let us continue with the boundary condition that we have. Let me scroll up. We have the RBF parameters, which are set to default itself. So let me scroll all the way up and have a look at the boundary conditions for the domain, that is the fluid region. We have the bar/domain, which is again a mapped contact interface. Next, we have the inlet boundary condition, which is going to be a velocity inlet, the type of the boundary condition. Let me show you what is the velocity magnitude. It's going to be 11.241 meter per second. So we have the outer and the symmetry boundary condition. These two surfaces are specified as symmetry planes. We have the outlet, which is a pressure outlet, which is modeled as a pressure outlet at atmospheric pressure. And lastly, we have the top/bottom, which is basically a wall boundary condition. Next, let us have a look at the interfaces which are present. We have one interface that is a mapped contact interface, which is present. And where do we define, the next question, where do we define that it's a FSI model, or how many, is it a one-way FSI or two-way FSI? This is defined in solvers. We have a tab for fluid structure coupling. And over here, as you can see, the FSI coupling method, we have both one-way and two-way. For this, it's going to be a two-way FSI. That is, the fluid is going to affect the solid, and the solid is in turn, the motion of the solid is in turn going to affect the fluid domain as well. Let me specify at last the stopping criteria before we run the simulation. It's going to be the maximum inner iterations are going to be 5. We have the physical time that we are going to run the simulation for 1 second as a whole, and the number of steps are going to be 1,000 steps. So lastly is having a look at the results. So firstly, let us have a look at the plots which are present. Once the solution is run, let's have a look at the plots. So basically, let's have a look at the plots in z direction, the displacement plot. So you can see the displacement of the beam. So basically, as the wind starts, it slowly starts oscillating and then it reaches its peak. So basically, we can see over here, on the y-axis we have displacement in the z direction in meters, and the physical time on the x-axis. So basically, we have the displacement of the beam in the sinusoidal motion. So the next one is to look at the scene. We can run the reports for displacement in C monitor, but what would happen is it would give us basically an instantaneous value at that particular time step. So that is not required. So let's have a look at the scenes. Let's have a look at the stress. That is a von Mises stress maybe. Let me open the scenes. Stresses, von Mises, click open scene. So you can see that we have the von Mises stresses along the lower, so basically the scale on the downside, you can see it's von Mises stress in megapascal, that is on the beam. And also we have superimposed the velocity vectors in a section along the y-axis. So you can have both these coupled to get a better understanding of what exactly is going on in your domain. So the last thing is to go ahead and create a volume rendering scene. And for that, firstly, we need to go ahead and create a resampled volume. Let me show you. So basically, a volume rendering is used to display the volumetric objects that are defined in the 3D domain. So basically, it's a closed entity where you are the resampling process basically generates an approximation of the result values that reside in the underlying 3D finite volume region that you create. So this is how it's created. You're going to specify all the coordinates and create a box. It's a no display because we already have a scene created. Let me close this. Let us go back to the scene where we have a vorticity scene, which is already created. We have in parts, we have the resampled volume, which we saw present in the derived parts. The scalar field is going to be vorticity in the J direction. And the maximum and minimum is -250 to +250. And the units is per second. We have that as a scalar field. We have volume rendering settings, which is direct volume rendering. And at last, let me show you. So basically, you can see, if you look at the vorticity scene over here, you can see a red star mark. So that means that that particular scenes are saved for every iteration or time step which we specify. I'm going to show you how that is particularly specified. We have the file format PNG of the image which is getting saved, and the trigger method. We have different trigger methods of which you would like to save the image from. We have iterations, we have time steps or delta time. We have selected time step for this particular one, and in update the time step frequency for every single time step we are saving the model. So let me open the scene for the vorticity and show you volume rendering basically. Right click, open the scene. For this particular final time step of 1 second, we have this particular scene which is created for vorticity. Similarly, you can save these images or maybe record a video as well. And that is what is going to be shown now. Hope you enjoyed this part of the Hands-on Simulate series. I will pass it back to Yafis to cover the flow-induced noises. If you have any questions, please don't hesitate to drop it in the chat or send us an email. Thank you.
Thank you very much, Mario, for that informative session. Give me a second, and I hope you guys all see my screen. So what we just covered was the fluid structure interactions portion in Simcenter STAR-CCM+, and now we're going to jump into acoustics. So, before I begin the section of acoustics, let's just start with the basics. What is sound? So sound is essentially small molecular vibrations in the medium at rest. So when energy is introduced in a system and the molecules vibrate, so as a consequence of those vibrations, we have some areas of compression and some areas of rarefaction, meaning that you will have high pressure or low pressure in these different regions. So this fluctuation is how essentially sound propagates throughout the mediums. So typically between the two maximum is what we call the wavelength, and which is a function of the frequency. So here in this image, we're seeing a piston that uses the energy to produce a vibration. The molecules themselves do not propagate. They vibrate around their resting position. but the energy is propagating, and that's what we see here. Similarly, on the other example, we have a cooling fan of an electric motor on an electric car model. We can see the propagation of the waves with the maxima and the distance dominated by the frequency. So let's break down the components of sound. First, we have the source. Now, this is something that introduces the energy into the system. Usually when we talk about acoustics, it's produced by vibrations, in the structure. A simple example would be, tapping your table. Another one would be a gearbox, which is vibrating and then radiating acoustic pressure, as shown here. Now, turbulence is, essentially a variation in pressure, which can also propagate through the environment. Hence, you can have turbulence as a noise source. And I'll discuss about this more in detail shortly. Now, after you inject the energy into the system, the next step is propagation. First, this can be an airborne noise. The fact that I'm talking here and I'm inducing pressure in the air, you can hear me under this category. Now, if I talk loud enough, someone may hear me through the window. That's because of structure-borne propagation. So the noise creates some sort of vibration in the structure, and those structural vibrations then induce noise in the other domain. Often in a lot of applications, we get a mix of these two types of propagation. Now, at the end, acoustic does not matter if we don't have a receiver. There's an expression that says a tree fell down in the forest. Did it actually make sound? So we need a receiver to capture that change in pressure. Essentially, these are the three components in acoustics, and we need to capture all three components when we want to simulate noise. So we will have to find a way to determine the noise, determine the source. We'll have to propagate the energy injected by the source into the system, and then we'll also have to tell the tool where we want to see the results, or where you have that microphone or air. But essentially, why bother understand acoustics in the first place? All right. So first, there's legislation on environment noise, such as those generated by vehicles. Vehicles need to be able to conform to tests such as the pass-by noise testing, as well as the acoustic vehicle alerting systems. Now, in products such as centrifugal pumps, washing machines, or vacuum cleaners, you want a low noise design, and that's what's desired. Just a moment ago, I mentioned how noise is essentially pressure perturbations and can be generated by turbulence flow structures. So in the space industry, the payload in a launcher is submitted to very high acoustic pressure. These generate vibrations, stress, and force levels in the payload structure, which could compromise its structural integrity. Now, noise generated by such turbulence is also a major concern for cabin comfort in cars, for example. I don't think we need to run a simulation here to begin with. Let's just say he needs a cabin to reduce the noise to start with. All right. So some more examples here that are essentially important for acoustics simulation. We have HVAC applications where noise is generated by the compressor. You have landing gear. You have pressure fluctuations by side view mirror, which can cause noise inside the car cabin. There is clearly some value in understanding acoustics, but how we, as I mentioned before, resolve an acoustic problem depends on the source and the medium of propagation. So let's look at the main types of noise sources and propagation method. So noise, as I mentioned, is generated by structural vibrations, like someone slamming on the table. Those such a noise is called vibroacoustics, right? But as mentioned earlier, noise can also be generated by turbulence through pressure fluctuations in the flow. So such flows or such flow-induced noise is known as aeroacoustics. Now, another method of noise source is through structural vibrations, which are induced by flow vibrations. So such noise types are called Aero-vibro acoustics. So to give you an idea here, you have flow, you have a structure. The structure induces some sort of pressure fluctuations. These pressure fluctuations vibrate the structure, and these structural vibrations then generate structure-borne noise. Now, there are also other types of noise sources. Today, I'll run through the various solutions to resolve such acoustics problems using the solutions available in the Siemens portfolio while focusing on just flow-induced noise. Okay, so let's now identify the different simulation tools available to resolve acoustic problems from a physics perspective. right? Firstly, let's start with a pure structure analysis involving only structural FEM model, right? So that's a pure structural analysis. We have Simcenter Nastran to resolve such simulations. Now think of vibrations on a gearbox due to excitation on bearing location that are coming from the shaft in the gearbox. Even by post-processing the pure vibrational results, we can get a first idea which areas are vibrating more, which frequencies seem to represent more in the vibrational response, and etc. Simcenter Nastran also supports ERP, that's an equivalent radiated power, which allows users to integrate the vibrational energy over the surface of the structure and obtain such the equal, obtain the equivalent radiated acoustic power. But here you make the assumption that the structure has a perfect radiation efficiency. Now, evidently, the next type of problem would be a pure acoustics problem, which is also supported within Simcenter portfolio. Here you can, run this acoustics problem. Could be interior or exterior, could be a FEM or a BEM method to solve the acoustic response. And within this package, to simulate such physics, it's important to consider that there is zero mean flow made as an approximation. So we're only consider noise that's generated by these structures, and essentially there is no effect by the flow in this type of simulation. Now, what we can do though is combine these two mentioned physics and arrive, of course, to a vibroacoustic problem. Now, this is a category in which you can find a lot of noise and vibration problems, such as intake ducts that exhibit not only orifice noise, but also shell noise. And there's also powertrain components that are excited by forces that are resulting in vibrations which emit these acoustic waves. Now, at the bottom left, we have the Aero-acoustics. Here we have, the noise that generation mechanism is captured, which involves more fluid dynamics physics, as we mentioned before. However, the noise propagation is considered also to be purely acoustic. So this can be captured within STAR-CCM Plus without the help of any other tool. Now, another flow-induced noise vibration application, as I mentioned before, was the Aero-vibro acoustics. Here, the flow imposes a fluctuating pressure on a structural surface, making the latter vibrate and radiate acoustic energy, like wind noise in the car or a train or a plane, even pump noise. So we can simulate these sorts of problems through a combination of Simcenter Acoustic and Simcenter STAR-CCM Plus. And then the last one is that's noise generated or emitted by electric machines. And this is a special case of vibroacoustics. It can be captured using the Simcenter 3D electromagnetics and Simcenter acoustics. But for today's presentation, we're going to focus on the Aero-acoustics and the Aero-vibro acoustics. So this is the orange box that was lying there all the while. So basically was to focus on that. We are going to, focus this presentation on just purely Aero-acoustics and Aero-vibro acoustics. So we'll, let's just begin and talk about the available technologies right now within the Siemens portfolio. So within STAR-CCM Plus, we have two available technologies to help resolve such acoustic problems. First is a pure, for a pure aeroacoustic problem, the source is essentially pressure fluctuations. Essentially, we can use CFD to resolve the flow in the time domain to get the transient pressure and help capture those acoustic sources. And the other hand, you also have a purely acoustic solution which you can use in numerical acoustics code within Simcenter Acoustics. It's essentially, the acoustic wave equation. Here we link the derivatives of pressure, time, and space to the speed of sound. Generally, we solve the equation in the harmonics domain. Now, these are the two main categories we will cover today. And so first, we'll look at the CFD side. All right. So the first method of resolving an acoustic problem would be the direct noise method. Now, it's an approach that requires solving the entire flow field for the full unsteady simulation. There are very few modeling assumptions and less work to set it up. Now, this can be done within STAR-CCM Plus. It requires a high numerical resolution to capture the spatial and transient effects of the acoustic pressure perturbation. It requires unsteady compressible CFD and turbulence models such as DES or LES. So let's see what that looks like. So here we're seeing the results of a flow around a car, specifically near the side view mirror. To the right, you have the pressure field, and to the left, you have, to the to the left you have the pressure field, and to the right you have the acoustic field. Now you can see that the hydrodynamic field or the pressure field is moving at much larger time scale than the acoustic field. Now, if you were to look at the pressure perturbation, to capture the acoustics field, we'll need a much higher resolution, which means larger mesh size, higher cell quality, essentially leading to longer solve times. Now, as an approximation, what we can do is we can split the source and the propagation calculations to make such simulations computationally efficient. So these methods are known as the hybrid methods. First, what we're going to do is we're going to look into the direct noise calculation method and why it's important to have these methods and why hybrid methodology is not valid in these situations. So when would you use direct noise calculation? So situations when it's necessary is when the measurements are measurement locations are very close to the source, as well as when there's a two-way coupled flow acoustic interaction. Some of the examples shown here is, if you can see the sunroof, there's a two-way coupling between the source and the propagation from the leading edge to the trailing edge. Flow duct whistling or buffeting, where it's very close to the source. But as I mentioned before, running such simulations are computationally expensive. Hence, we have the other method to resolve acoustics, especially when we want to resolve acoustics in the far field. So imagine if you were to resolve these acoustic pressures in the far field, it'll just be too computationally expensive. So one way, to resolve this method or resolve far field noise is using hybrid methods. But before I jump into hybrid methods, I do want to point out something. Within the support center, there's an article for best practices. Basically, running a direct noise calculation is all about running the high fidelity simulation. So all the details regarding the geometry quality, the turbulence models, mesh size to capture those pressure perturbations responsible for the acoustic signature is all provided in that article. For those who do not have access to the support center, please don't hesitate to contact me right after this, and we'll make sure that you do. So putting direct noise calculation aside, let's move right into hybrid acoustic simulation methods and understand this decoupling of sound generation and propagation. Now, like I mentioned, we want to decouple where the sound is generated and how it propagates. So let's look at it through an example of an airfoil. Now, if we want to capture the sound generation and propagation, particularly in the turbulent region, we have to resolve it using the Navier-Stokes equation. However, in the propagation region, the pressure distribution is less complex. As you can see, close to the source, you'll have a lot of fluctuating irregular pressure acoustic waves. But as you go away from the source, you're going to see that the region becomes less complex. And in these areas, you can essentially use a linear wave operator, which links the derivatives in time and location to the speed of sound. So, but there's an issue. If you look at a linear operator, there's essentially no source term. However, if we combine with the mass and momentum equations and transform them, we generate an equation that's very similar to that of the wave equation. Except here we have a source term. And this term was first discovered by Lighthill and is called the Lighthill tensor. So this tensor is used to describe the acoustic source. So looking at just the tensor formulation, when Lighthill provided this formulation, it was only valid in the absence of solid surfaces. Then Curl introduced a formulation which was valid for steady surfaces. Then you finally have the Fox, William, and Hawking formulation that is valid in the presence of moving surfaces like fans or rotating bodies. So the idea over here is to transform the source using the CFD results to the equivalent formation to calculate the propagation of the wave. All right. So just to go back to the airfoil example, what that means is to capture the field noise in the near field, we captured the turbulent pressure field accurately using CFD. And in the far field, we use one of these different formulations I mentioned above, or just mentioned in the previous slide, to capture the sound propagation. So what we're going to do is we'll just see how this works using the Fox, William, and Hawking decoupled analysis. So in the Fox-William method, we calculate the sound source on the boundary and then use a surface integral to solve the radiation part of the calculation. So when would you use this? This is when the far field pressure is less complex. You have, an acoustically compact source region. What that means is that the source region is relatively small compared to the wavelength. But within the Fox, William, and Hawking method, you have two given workflows. First is the impermeable method, where the sources are calculated on the surface itself, right? So the surface integral is used to calculate those radiative forces or the sound sources. So applications would be fan noise, propeller noise, any sort of helicopter rotor blade noise. But what if you want to take into account the turbulence in the wake or the noise generated by the turbulence in the wake? Then you have the permeable method. And over here, you consider a source surface that's encompassing the wake and then calculate the radiative forces on that wake. So, examples used is jet noise and exhaust noise. Now, there's also another decoupled model, which is important, is the acoustic wave model. Now, this is where you solve a PDE for understanding noise. So using this method, you solve both the incompressible CFD and an acoustic wave equation. The acoustic sources are calculated from the hydrodynamic pressure, and then based on the acoustic perturbation model, we would model the propagation sources to the environment. So when do we use it? Again, when the observer is in the near field, low Mach numbers, and separate hydrodynamic and acoustic pressure. Now I'll explain a bit shortly why these limitations are, but some of the examples that you use it would be the side view mirror generating turbulence, and if you wanted to see the sources essentially by an acoustic wave. So any sort of pressure fluctuation on a given surface, and you want to see how those are generated within the domain, you would use the acoustic wave model. So going back to these decoupling and decoupled analysis, I just want to talk about the advantages and disadvantages. So advantages. Now, one of the main advantages, you're trying to capture all the effects, you're capturing turbulence, and it's all available within STAR-CCM+. So all these methods that I talked about are inbuilt within STAR-CCM+. But then when we want to look at the disadvantages, we have a few. First, it's computationally expensive. You will have to resolve those near surface forces, and you have to have high accuracy to capture the acoustic effects. As we saw, the acoustics source term in the pressure perturbation is quite minimal, so you have to capture all that. And then also, there are some limitations for acoustic engineers. Now, there isn't any strong coupling with structures, and you cannot have absorbent materials. Now, the question arises now, since we're already decoupling the analysis, if you're using one technique to solve the source term using CFD and another technique to resolve the propagation of the sources, why not leverage the advantages of these two techniques? That's one being computationally efficient, and the other being being able to capture those effects. What we can do is essentially convert those source terms into acoustic terms. So if we were to take those source terms that's generated by those surfaces and convert them in acoustic term, what we would see here is in the Lytle equation, the source term is equivalent to a quadrupole. In the Curl equation, we have the source term equivalent to a quadrupole and the dipole. And in the Fox-Williams and Hawkins equation, we can see that it's an equivalent convected quadrupole and convected dipole. So if we are able to convert these source terms into 3D acoustic sources, then we can use acoustic codes to resolve them and not need CFD to resolve them. So let's first look at these typical acoustic sources. First, you have the monopole, which is basically a pulsating sphere. So such sources are associated with wafts being periodically pushed by the flow. Now they correlate to the fourth order of velocity. Then you have a dipole, which is essentially like a moving sphere. These forms of sources are associated with interaction of the flow with steady surfaces. So like we mentioned the Curl methodology, and they correlate to the sixth order of velocity. And finally, you have these complex quadrupoles that are associated with free turbulence of the flow, and they correlate to eighth order of velocity. Note that as we just mentioned, the pressure fluctuations associated with quadrupole is proportional to a higher order velocity, hence they're more prevalent at higher speeds. Now, if we were to go back to the three types of flows, we saw the no surfaces. Where there are no surfaces, they correspond to Lighthill, uh, to source term, the steady surfaces to Pearl, and then the moving surfaces with the Fox Williams Hawking. And we could essentially convert these into the representative uh, acoustic sources. So no surfaces, quadrupoles. With steady surfaces, we have dipoles and quadrupoles in the wake. And then with the moving surfaces, we have rotating dipoles with quadrupoles in the wake. But let's say we assume that the Mach number is less than 0.3. So what happens here is because the quadrupole of sources are two orders higher than dipoles, let's say at 0.3 Mach, the quadrupoles, that's 0.3 into whole square, is about 0.01. It represents less than 1% of the noises that are generated. So at low Mach numbers, basically, uh, the noise is just dominated by dipole sources on the surface. So in these cases, we can essentially ignore the quadrupole uh, sources. So going back to the two methodologies, we talked about, CFD, but we can basically use a numerical acoustic code to resolve those acoustic sources. So these equations are typically solved in the harmonics domain, which is quite efficient as you can resolve the frequency range of interest only. So essentially, we're going to talk about the numerical acoustic code within Simcenter Acoustics, and especially when resolving Aero-vibro acoustic analysis. So let's see how that can be done. So the idea over here in a vibroacoustic analysis is that first you want to resolve the flow using incompressible or compressible CFD package, and then calculate the equivalent dipole sources by the pressure fluctuations on the surface. And then based on the pressure fluctuations on the surface, you will convert that into a frequency domain and solve the Helmholtz equation for a coupled vibroacoustic analysis. So where would we use this sort of application? So essentially, we can use it for both near and far field. It's only applicable for low Mach numbers because that's when the effect of quadrupole sources are not high. Note that quadrupole sources are domain-based sources, so you have to resolve the full flow volume domain if you want to capture those, which makes it computationally expensive. And that's why making this assumption of them at low Mach numbers is advantageous to us, is because we don't need that much of a high resolution in the domain. But also, one advantage is that because you're using an acoustic code, you can add absorbers, you can couple it with structures to analyze insulation effects. And a typical application that we'll see soon is the HVAC industry, fan noise, understanding side view mirror noise. So let's jump into what this workflow looks like and how we would couple the STAR-CCM solution with the Simcenter 3D acoustic package. So the workflow, like I mentioned, is a combination of STAR-CCM Plus and Simcenter 3D Acoustics. The first step is to solve the flow domain using a high fidelity turbulence model. We'll use LES or DES simulation. You can use a non-compressible flow just to save time. Then we capture the pressure fluctuations on the free surfaces of that given body, and export that into a CGNS format. Now, the idea of exporting that into CGNS is so that we can import it into Simcenter 3D and map it into the acoustic mesh. We can generate the dipole from the pressure fluctuations. So convert that pressure. Let's say you have a transient pressure acting on a given surface. You convert this transient pressure into equivalent dipoles, and then essentially just solve for the vibroacoustics model using the Helmholtz equation. It's as simple as that. So let's see how we can resolve this with regards to an HVAC duct using this method. So note that this approach again is only valid at low Mach numbers, so that there's no noise generated by the turbulence, as the quadrupole sources is negligible. So the first step would be running that transient CFD simulation. But before we begin running the full CFD model, you want to run a initial CFD mesh based on experience essentially, and you want to capture the pressure fluctuations. In our mind, we want to capture the pressure fluctuations by this flap in this HVAC duct and the free surfaces of the duct itself. So once you've run you've created your initial mesh, you run a steady flow analysis. And the reason why you do that is because it's less time consuming than a transient analysis. You can get the pressure field on from the steady condition, which will give you some sort of feedback on the mesh resolution. And it's also a starting condition for your transient analysis. It also gives you information on the sound sources to help improve the mesh. So from the steady analysis, we can clearly determine that the sources are majority of that is around the bend and due to the flap. Using this information, what we can do is then essentially improve or refine the mesh in these regions. And it's important to know that the areas where you see the propagation, in the outer region, you have a much coarser element, as you don't need a detailed flow to capture that propagation of the acoustic wave there. We're going to use the acoustic wave equation to do so. We just need to capture the source region pressure perturbations essentially. Then, you apply for the whole domain. You can apply a free stream boundary conditions on the outlet for the flow to pass through, and you can see the gradual coarsening towards the boundaries. So once you've set this up, you didn't run a transient result. So this is an LES simulation to capture the pressure fluctuations around the duct and the flap. The idea is here is that we're going to extract the pressure fluctuations acting on the surface pressure and then export them into Simcenter Acoustics. So let's just see how that's done. So here are some of the pressure results on the free surfaces. So we're looking at the pressure results there. We can use an auto export command to send the CGNS files on the boundaries to the source. So the format that we, so basically you go to File and hit Auto Export. What you're going to see is, a feature to export the results at any given trigger. Mario had shown how we can, export data using scenes. Here we're exporting data within the domain. So the file format that we're going to use is a Siemens Virtual Lab custom CGNS file format. And the field function is going to be pressure. We select the boundaries, that is the faces of the duct as well as the flap. And then we select the trigger to extract that data. And the trigger is every time step is going to create a CGNS file, and each CGNS file is exported with that pressure data. So if you want to just recap to the workflow, we resolve the transient simulation in STAR-CCM Plus. Now we're going to import that CGNS file into Simcenter Acoustics to capture that acoustic vibration. So I won't go much detail into how that's accomplished in Simcenter Acoustics, but I'll just give you an idea how that can be done. So the first thing that you need to do is create the acoustic mesh. So the considerations that you have in doing the acoustic mesh is at least have 6 elements throughout a wavelength, but you also have the FEMAO method, which can increase the element order to improve the quality of a mesh, reducing it down to 1 or 2 elements per wavelength. You have a mushroom shape structure for calculating the radiation across that surface to essentially to represent the radiator surface, but also then you can create surfaces or microphones to visualize the data. As you can clearly see, the mesh for the acoustic mesh is much smaller than that of the fluid mesh, as you don't need that high resolution over here. So we're not worrying too much about that. So once you've created the acoustic mesh, the next step would be doing the CFD pre-processing. The first thing would be importing or mapping this, the CFD data onto the acoustic mesh. It uses a distance-based method, and it has a conservative algorithm to conserve energy, even when you have a coarser mesh in the acoustic phase. The next step would be to convert the pressure fluctuations on the surface into sources using a FFT, Fourier transform. And essentially, this is what it looks like. So we took the CFD data, and using a FFT transformation, we converted that pressure fluctuation into equivalent dipole sources. So once you've done the pre-processing, the next step is the solution setup. So we define the input data for the source generation. Over here, you can select compressible or incompressible. So input data is basically those equivalent dipoles that we just calculated. And then you can add also absorbers like acoustics absorber if needed to define the radiative conditions of the mushroom. And finally, we define the requested frequency where where we want to calculate the data. And in this method, we actually request 120 frequencies, and this calculation was done in less than 5 minutes on a laptop. So this method is obviously more suited towards capturing tonal sounds on frequency that you're looking for than essentially broadband noise. But as I mentioned, it has fast calculation time, so it's not much of an issue. The last step would be post-processing. So once the solution is resolved, you can essentially post-process all the results within Simcenter 3D. Typically, you're going to look at contour plots. We can deform the mesh to look at any directivity pattern on the noise as well. Of course, you can see the frequency spectra at various points. Due to time constraints, I could have shown you that in the tool itself, but I'm just going to skip that and just basically just show you a quick understanding that all of this is possible when you're looking at here. We're looking at different frequencies, at different radiation pattern. This is in megapascals. We can just quickly change that to the dB scale, which makes more sense, of course. We can run through a set of frequencies, change the display if you want to recognize any certain features. We can also look at specific face angles to deform the mesh based on the pressure data. So by looking at that, essentially we can see where the acoustic pressure is radiating, and we can see some rotation pattern. But not only that, but you can also animate the results through those modal responses. Of course, you can also then create XY graphs to look at spectra data and create points to see frequency spectras, for example. So all of this is pretty much available within through this couple solution. So just going back to the process over here, this was the workflow. Just to give you a quick recap, we ran a CFD simulation with STAR-CCM Plus, took the pressure fluctuations, imported that data into Simcenter 3D, and ran a vibroacoustic model. Now, we can also, for example, take installation effects into consideration. So let's say that duct was a part of a vehicle or a car. You just don't need a new mesh. You just don't need a new mesh for the duct. You just need a new mesh for the cavity. And you can take the full cabinet into account with reflection on the boundaries. You can also include acoustic observers, so basically a person over there. And the pre-processing is the same. It just creates a different mesh. And because you're running an acoustic mesh, it's pretty fast. The solve time is less than 1 minute per frequency in capturing, looking at how those duct noise propagates within the domain. So another example other than HVAC, you could also use it is for noise generated by a windshield. So you have these pressure perturbations that are generated due to the side view mirror. Those side view mirror pressure perturbations cause some sort of pressure response onto the windshield or the side, the windshield. And so what happens is that you have these surface pressures that are fed back into Simcenter Acoustics, so that you can understand the acoustic behavior within the interior of the car. So essentially, there are a lot of possibilities in how you would like to conduct an acoustic analysis. So quickly going through the summary of what I just showed in today, we can understand aeroacoustics as it's becoming more and more important, especially with electric vehicles, where side view mirror noise is more loud than that of the powertrain. Then you also need to be able to decouple the source term as well as the propagation to make it more computationally effective, which is pretty much possible with the given workflow that I showed today. Then we talked about the sort of decoupling, not only through Aero-vibro acoustics, but also just looking at using Fox-William-Hawking method and the acoustic wave solver within STAR-CCM Plus to do that sort of decoupling. And then finally, I just introduced the hybrid approach of where we leverage both CFD and